Consider two monsters, so powerful that they can devour anything in their path, even light itself. Now imagine these monsters meeting each other in a cosmic dance of death, creating a cataclysmic explosion that shakes the very fabric of space and time. What would you see? What would you hear? And what would you learn from this epic encounter? Hello everyone. Welcome to another exciting video on our channel, where we explore the most amazing mysteries of the universe. Black holes are the most extreme objects in the cosmos. They are so dense and have such a strong gravitational pull that nothing, not even light, can escape from them. They are invisible to our eyes, but we can detect them by the effects they have on their surroundings. But what if two black holes meet and decide to dance? What kind of cosmic fireworks would they create? How would they affect space and time itself? And what would we see and hear from Earth? In this video, we'll show you a stunning computer simulation of two black holes colliding, based on the latest scientific data and theories. You will witness one of the most violent and spectacular events in the universe, and learn some fascinating facts about black holes along the way. But before we dive into the simulation, let me ask you a question. Do you know how big a black hole can be? Well, there are different types of black holes, depending on how they form and how much mass they have. The smallest ones are called primordial black holes, and they could have formed in the early moments of the Big Bang. They could be as tiny as an atom, but with the mass of a mountain. The most common ones are called stellar black holes, and they form when massive stars die in supernova explosions. They can have masses ranging from a few to tens of times that of our sun, and diameters from a few kilometers to hundreds of kilometers. The biggest ones are called supermassive black holes, and they lurk in the centers of galaxies. They can have masses from millions to billions of times that of our sun, and diameters from millions to billions of kilometers. But there is also a mysterious type of black hole that has been elusive to astronomers until recently. They are called intermediate mass black holes, and they have masses between hundreds and thousands of times that of our sun. They could be the missing link between stellar and supermassive black holes, but how do they form? One possible way is by the collision of two smaller black holes, and that is exactly what we are going to see in this simulation. What happens when two black holes collide? When two black holes orbit each other, they lose energy by emitting gravitational waves. These are ripples in the fabric of space-time that travel light and carry information about the sources that produce them. They emit more and more gravitational waves until they eventually merge into a bigger black hole. This process is one of the most powerful events in the universe. It releases more energy than all the stars in the observable universe combined. It also creates a huge distortion in space-time that can be detected by special instruments on Earth. The first direct detection of gravitational waves was made in 2015 by LIGO, which is Laser Interferometer Gravitational Wave Observatory, a pair of facilities in the United States that use laser beams to measure tiny changes in the length of two perpendicular arms caused by passing gravitational waves. Since then, LIGO has been joined by Virgo, a similar facility near Pisa, Italy. Together, these observatories have detected dozens of gravitational wave signals from merging black holes and neutron stars, which are dense remnants of exploded stars. But none of them was as spectacular as the one detected by the signal, named GW190521, which was produced by a collision between two giant black holes, one with a mass of 85 times the mass of the Sun, and another with a mass of 66 times the mass of the Sun. The merger resulted in a new black hole with a mass of 142 times the mass of the Sun, and released an energy equivalent to 9 times the mass of the Sun in gravitational waves. This event was mind-boggling for several reasons. First, it was the most powerful, most distant, and most perplexing collision ever detected. It happened about 7 billion light-years away from Earth, when the universe was half its current age. It was so powerful that it shook space-time like never before. Second, it involved a black hole with a mass that was thought to be impossible. The 85 solar mass black hole fell into what is called the pair instability gap, a range of masses between about 65 and 120 times the mass of the Sun, where no black holes should exist. That's because stars in this range become so hot in their cores that they start converting photons into pairs of particles and antiparticles. This causes them to explode violently before they can collapse into black holes. So how did this forbidden black hole form? One possibility is that it was itself the result of a previous merger between two smaller black holes. Another possibility is that it was formed from a very massive star with a very low metallicity, meaning it had very few elements heavier than hydrogen and helium. This would make it less prone to pair instability and more likely to collapse into a black hole. Third, it created a new black hole with a mass that was never seen before. The 142 solar mass black hole belongs to the elusive category of intermediate mass black holes, which are thought to be the seeds of supermassive black holes. But until now, there was no conclusive evidence for their existence. But this event could be the first direct observation of an intermediate mass black hole and a clue to how supermassive black holes form and grow. But what does a collision between two black holes look like? How can we visualize something that is invisible to the eye? Well, thanks to the power of computer simulations and advanced visualization techniques, we can get a glimpse of what happens when two black holes collide. The simulation was created by scientists at NASA's Goddard Space Flight Center using powerful supercomputers. It shows what would happen if two stellar black holes with different masses orbit each other and eventually merge. This simulation shows what a human observer would see if they were close enough to witness a collision between two black holes. The simulation uses a technique called ray tracing, which traces the paths of light rays as they bend around the warped spacetime created by the black holes. The simulation also shows the gravitational waves emitted by the merger, which appear as ripples on the surface of a sphere surrounding the observer. The colors on the sphere indicate the strength of the gravitational waves, with red being the strongest and blue being the weakest. The simulation starts with two black holes orbiting each other at a distance of about 15 times their diameter. The black holes have different masses and spins, which make them appear distorted and asymmetric. The smaller black hole has a mass of 36 times the mass of the Sun and spins clockwise. The larger black hole has a mass of 29 times the mass of the Sun and spins counterclockwise. The faster spin of the smaller black hole makes it look smaller in size, while the slower spin of the larger black hole makes it look bigger in size. As they orbit, they emit gravitational waves that carry away energy and angular momentum. This causes them to spiral inward and increase their orbital speed. The gravitational waves also create a Doppler effect, which makes the black holes appear brighter when they move toward the observer and dimmer when they move away. As they get closer, the gravitational waves become stronger and more frequent. The black holes also start to deform each other more significantly due to their tidal forces, The smaller black hole stretches into an elongated shape as it approaches the larger one. When they reach a distance of about 3 times their diameter, they enter what is called the plunge phase. This is when they rapidly fall toward each other and merge into a single black hole. The merger produces a powerful burst of gravitational waves that shakes space-time like never before. The newly formed black hole has a mass of 62 times the mass of the Sun and spins rapidly in the same direction as the smaller one. It also has some residual wobbling motion due to the asymmetry of the merger. This motion causes it to emit more gravitational waves as it settles down into a stable state. But wait a minute. The 2 black holes individually had total 65 times the mass of the Sun, with larger one being 36 and the smaller one being 29. Whereas the newly formed merged black hole has mass of 62 times the mass of the Sun. So where did the other 3 solar masses go? They were converted into pure energy in the form of gravitational waves during the merger. This is an incredible amount of energy, equivalent to about 5.4 multiplied by 10 to the power of 47 joules, or about 10 to the power of 29 times the annual energy consumption of the entire human civilization. This energy was released in a fraction of a second, making this event one of the most powerful explosions in the history of the universe. This is an example of how mass and energy are interchangeable, according to Einstein's famous equation, E equals m multiplied by c squared, where E is energy, m is mass, and c is the speed of light. This equation tells us that a small amount of mass can produce a huge amount of energy, and vice versa. In this case, 3 solar masses were converted into gravitational wave energy, which carried away information about the properties and dynamics of the merging black holes. The final black hole appears as a dark shadow surrounded by a bright ring of light. This ring is called the photon ring, and it is composed of light rays that orbit around the black hole at very close distances. Some of these light rays escape, while others fall into the event horizon. The photon ring also has some interesting features that reveal information about the properties of the black hole. For example, it has multiple layers that correspond to different numbers of orbits around the black hole. It also has some bright spots that are caused by lensing effects, where light rays from behind or near the black hole are magnified and distorted. This simulation is based on a simplified model that assumes the black holes are non-spinning and have equal masses. In reality, the situation is much more complex and chaotic, as we have seen with the event. But this simulation gives us an idea of what a human observer would see if they were close enough to witness a collision between 2 black holes. Of course, this is not something we would recommend, as you would be torn apart by the extreme gravity and radiation before you could see anything. But thanks to the power of science and technology, we can observe these events from a safe distance and learn more about the nature of black holes and the universe. So what do you think? Are you amazed by the beauty and violence of black hole collisions? Do you have any questions or comments about this topic? Let us know in the comments section below. And if you want to learn more about black holes and other fascinating phenomena in space, make sure you check out our other videos on this channel. We hope you enjoyed this video and learned something new. If you did, please give it a thumbs up and share it with your friends. And don't forget to subscribe to our channel and hit the bell icon to get notified of our latest videos. Thank you for watching, and see you next time.